Well, it's my pleasure to introduce André Carvalho from University of Paulo, who will talk about the structures on 1, 2, and 3 manifolds coming from dynamical systems and impressionistic overview.
So, thank you very much for having me here. Thanks, Alex, for inviting me. And, I like Warsaw very much. People say that Krakow was much nicer because I love Warsaw. Okay, so I'm going to make a little personal remark here that today is my son's 20th birthday, so I put him there because I'm not going to be with him. He's in Brazil, I'm here, but anyway, I put him there just to celebrate his 20th birthday. Okay,
is he listening to us? Is he listening to us?
I don't think so. He's in class actually, but he's listening to some economic something or other. Just use the stuff that we do. Anyway, so what I want to discuss is well, like it's in the title, it's an impressionistic book. So yes, there will be pictures, like Felix said. And the idea is to present several instances of the same construction, the same idea that leads from some exponential growing feature of a dynamical system. So you have some self-map of a base, and it has some feature that grows exponentially, and this somehow produces a canonical or canonically associated structure on the underlying space. Okay, so that's the idea. So here's the first instance. The first instance is in one real dimension, and this goes back to the work of Miller and Thurston on multimodal interval endomorphisms. So you call so I here is interval 0, 1. You have a multimodal map. A multimodal map is just some map of some self. So this is the graph. There's some graph that goes up and down, or goes up, down, and down, up and down again. But it can only do this finitely many times. You don't want an infinite number of monotone pieces. You only want, so here there are 2 monotone pieces, 3, you want finitely many such. And you call the lap number the number of monotone pieces. And then you cook up some number which is the limit of the nth root of the number of monotone pieces of the nth area. So this is something that is clearly, well, you can do a computation, it's clearly this limit exists. And you will define this limit to be the growth number of it. So here's the theorem. See, this cannot be good,
I need to know.
I should also do the same for you. So we define a measure on the interval by essentially measuring. So you iterate f and you restrict to an interval, and you divide that by the number of laps of the nth iterate on the whole interval, and you take the limit as this goes to infinity. This is not quite right. You really have to do some power series. There's something else to be done here. But essentially, it's this: you take a multimodal map, iterate it, it has more and more pieces that go up and down. You count the number of pieces that go up and down inside of an interval. You compare this to the whole interval, pass to the limit, and that gives you some notion of mass of that interval. So this is a measure on the interval, and then you normalize it. You have measure 1. And so this measure now it produces also a way of semi-conjugating, really. The original map that you had Okay. So that semi-conjugates this map that was, not, in fact, at this point, the only thing we need to talk about here is the topological structure of the interval. Okay? And all of a sudden, out of this dynamical limit here, you get some gross number, and then you get some sort of a measure, and this makes the interval, or it gives a measure to the interval. You collapse the interval with measure 0, and that produces a geometric structure. On the interval, a measure which is monatomic and positive on open sets becomes a geometry. That's an interesting point. And with the geometry, the map now becomes a geometric map in the sense that it's piecewise linear. It grows, it becomes of the semi-conjugate, the original map to 1, which now is geometric in the sense that now there's a geometry on the interval, a length, and this length is expanded by the factor s and expanded by the factor minus s, or orientation reverse, and expanded again by the factor x. And likewise, you have the situation there. Okay, so this is something that, so this is the theme of the talk. You start with something which is merely topological, and it produces a geometric structure on the interval, which comes from a measure, and then the map becomes geometric in the sense that it becomes piecewise linear in this context. Okay, so that's the first example, and I didn't quote this is Milner-Thurston's theorem from the late 70s. Okay, so here's a second instance of the same general sort of phenomenon. The context is apparently different, but here's a different situation. You look at the closed states, the closed surface of genus bigger than 2, and you look at its fundamental group G, and you choose a set of generators from this fundamental group, and measure the word length with respect to the set of generators. And then you declare G, or you define G sub n to be the set of group elements which have length exactly n. And then
the shortest.
The
shortest length.
Yeah, the word is right.
The shortest word.
The shortest, yeah. Yeah, this norm here, the shortest word representing G. And then you define the set of elements of order of length exactly n. And again, you count the number of elements of length exactly n, take the 1 over nth power and take the limit. And that again defines a growth number for the group. So now you have some dynamically defined number, which is this so-called, again called growth number of the group. And well, so you have introduced this word here, which I'm not going to define this. Well, this group, provided the genus greater than 2, this group is so-called Gromov hyperbolic. It has thin triangles. There's some definition behind here, which I don't want to get into. But the point is that Gromov hyperbolic groups have naturally defined spaces at infinity, which for groups of surfaces are circles, a topological group. Okay? But this is again, Gromov hyperbolic space produces a topological boundary at infinity, which acquires a measure in essentially the same way. You count the number. So if you look at the circle at infinity, here I drew it very round, but it starts like only a topological circle, and you count the number of elements that is very close to any little arc over here. You divide by the total number of elements of length n, you pass to the limit, and that's again a measure, which on one-dimensional space is again a geometry. So this measure is not a quantum because of what it says, etc. Okay? So Right.
What is the analogy? Could you explain the analogy between this picture and the previous picture?
In the last line.
Well, for example, I'm using the same letter S here. So, yeah, there's a dynamical system on the first picture. Here, the dynamical system became a group and a group action. Right. I'll get to dynamics in now. So the group acts on itself by left translation step. And then there's a dynamics induced on the circle of infinity. And with this measure here, so this is a natural construction for a measure of infinity. And it turns out that if you look at the left action at infinity by the group naturally acts on itself, and therefore it acts on the dynamic infinity, it becomes, so this, with respect to this measure here, or this geometric structure, the action at infinity becomes PL. Not only that, so the group is like all the iterates of the dynamical system in the first context. And what happens here is that the expansion factor are always all powers of S of this growth number. So in a sense, so we have again a dynamical system now acting on a one-dimensional space. The dynamical system is not iteration anymore, but it's a group action. And this group action now, with this measure, or this metric now, it becomes a metric on the thing. And the expansion factor for the metric is constant, equal to S or some power of S. Just as in the previous.
This corresponds to maximal measure from the previous book.
Exactly. This corresponds exactly. Precisely. This is sort of trying to be the measure of specific.
Weights are just constant.
Weights are constant. Does that more or less answer the question? Or not really?
I think it is called conformal measure.
There is the analogy is in the phenomenon, but I thought maybe there is a more delicate level. So I didn't see let's say the word metric in the first picture, something like this.
Right. Well, the word metric there is the iterate N, the analog, right? But and yes, you can't dig much deeper into these analogies. You can do several things, but this again is an impressionistic thought. Okay.
So this action is faithful in the sense that non-trivial elements act non-trivially.
Yeah, the action of the group on itself.
On this circle.
Yes. Okay, so here's so since there's an impressionistic talk, and I'm going to change subject yet again, and talk about yet another instance of the same sort of mantra, the yoga of these linear groups. Okay, so here's a apparently different story, which is the following. So we start with a braid on 3 elements, for example. We take 3 points and then you move them down here. That's just a braid. You think of it made of wire, long wire. Stack this braid. Let's say you stack it infinitely down or infinitely up. So now N here is analogous. The analogy with the word length and with the iterate. Now there is in the first example is the stack where you're at. Okay, so you stack this infinitely up and down. There's sort of a Z translation up and down here. And then you take this braid and then you make it of wire and then you put a rubber band. Okay? And then you start pushing it down. Okay, so you put a rubber band here, push it down, it becomes this, you push it down again, it becomes this, you push it down again, and it starts to grow. And your rubber band is not, maybe you put it in some fear that it can't kind of cross itself, so you just push it down and down again. So the question is, what are these numbers here? So I'm cutting from these points out to infinity, say, and counting the number of intersections with the blue rubber band. Okay, so there's one here and one there. Here there are 2 and there are 3. Okay? So here there are 5, and there are 8, and there, and anyway, so there's 3 there, and here there are 8, and what are those?
The connection numbers.
Right. I don't know which exactly they are, but they're Fibonacci. Okay. And all right, so if there are Fibonacci numbers there, then you can maybe find the golden mean and then divide by the power of the golden mean or something. And then again, you can do this thing. So you have some exponential growth, and these numbers are the Fibonacci numbers, and then you divide something, or you can put Dirac masses on the very intersection here, and then you pass to the limit. And in the limit, when you see along, these dotted red lines here, or it's something converging to some sort of a measure. Okay? And the measure is, anyway, so the way to describe this precisely is that you say that in the limit, what you get is a transversely measured foliation or lamination, foliation or lamination, depends on how you want to view this, on the spheres. I'm thinking of all the planes. So I'm thinking of the ray that's really living on a plane, and I put 3 points on it, and then I push it down to the next plane, the next plane, and the next plane. And then when you obtain the limit here, is some lamination of the space or some foliation of the plane, which is transversely measured. Okay.
So I didn't understand how you obtain the measure. So you start with 3 points, push it down. On the picture, still 3 have
So all of the measure. So you're taking the limit off the rubber band.
Oh, I see.
Okay. So the rubber band is converging to a limit. You start looking at this, and if you push 1 or 2 steps down, and you take your glasses off, in my case, then what you see is some picture of a foliation. Okay? So that's the foliation, but not just that. The foliation has this transverse structure which you can measure sets, right? I mean, if you put these guys over there, you can see 5 guys here that map to here, and then there are 3 others down the left somewhere. And so there's this notion of putting things across, and that's the whole harmonic variant transverse measure. Okay. Okay, so this is again.
But here you consider break with this repeated pattern, right? So it's like
yes. No, this is again a dynamical system. Okay? So this is sort of yes. I'm not stacking different breaks.
Okay.
I'm not playing that game.
Yeah, but because I thought that you consider more general breaks, which are just and still that you will necessarily get the limit.
Stacking
different. That's fine.
Yes. I haven't, not in that. I'm stacking the same one, and this is the dynamical system again. In fact, another way of talking about this is as the isotropy class relative to these 3 points of a homeomorphism of the plane. And then I'm generating this homeomorphism several times to the future. And in the future, this thing converges to a measured lamination or a measured foliation in the limit. But you can play the same game backwards. And what you get is not the exact same picture. You get a similar picture, but which is transverse. So in fact, there are 2 limits here, one in the future and one in the past. And what you get in the future and the past, you get now 2 foliations which are transverse everywhere, except at the points off the break. So, and then you get 2 measures, a measure in a transverse measure in the infinite future and a transverse measure in the infinite past. But since the laminations themselves are transverse, what you get is you can hook up a product measure on the space. And a product measure on the space becomes actually a structure on the surface, on the plane here, or more generally. So what did I say here? So okay, so the upshot is that you get
the picture which disappeared already was related also with construction of Poikina attractor.
So this is exactly the Poikina attractor, which may talk about in any case. But this turns out to be precisely the Poikina attractor, but from a slightly different point of view, because the Poikina attractor has this differentiable structure to it.
No, but I mean topological.
Topologically, this is precisely the Poikina attractor. And it's also the quotient of, so if you take the 2, 1, 1, 1, acting on the plane, and then you mod this by Z2, take mod Z2, and then you get the torus, and then you get some map here FA, and then you can mod further by Z goes to minus Z. Z goes to minus Z, and this becomes a sphere with 4 singular points, which are, and then you get from that here CA. And you know, these two foliations are exactly the stable and unstable foliation. So that's okay. The problem with describing it this way, which you know probably familiar to most of you, is that this already comes with with the Euclidean structure of R2, and then you project it down to to some structure on the torus, and then you project it down to another geometric structure on the fluid sphere, which is Euclidean, except that it has 4 points where the angle is 5. Okay, but it's a nice structure on the sphere. Okay? But what I'm sort of describing here is a sort of from first principles way. You start with the topology of this braid alone, and you can recover in this dynamical way. You can recover the geometry of the plane, or the torus, or of the sphere for the spectral point. So this you get it all out of that. And so, right, so what I said, the upshot that you get these 2 transverse measuring foliations with finitely many singular points. And right, so as I just said, there's a type. So in this type of scheme here can be found much more generally. So this is due to Thurston's classification of surface homomorphisms. You start with the homomorphism or the isotopic class of a surface homomorphism, and then you play the same game. Well, I mean, there are 2 situations that were simpler, but in most cases you get some. If you have a composition of Dane twists on a surface like this, typically what you have is some exponential growth, and then you find 2 laminations in the limit. But not only these are laminations, but they have transverse measures. And all of a sudden, you started with the topological surface and the topological map, and you get some measure, some actual geometric structure on the surface. Okay, so you get some geometric measure, and the map becomes again piecewise linear. In fact, it's linear, and it's linear with that growth number here. Well, one of the directions is expanded by the growth number, and the other is contracted. Okay, so there. So right, so this is the topological to geometric path, but so there are other. So this connects with other areas of mathematics, like real surface theory. Right? So this geometric, the conic flat structures on these surfaces are really homomorphic or meromorphic quadratic differentials living on a real surface a real surface structure on the topological surface. Right? And the map, this linear map here, becomes what's called a triangular mapping of structure associated with such a quadratic differential. Okay. All right, so there's a comment here about pseudomorphism. These things are called pseudomorphism maps, and they come. So these integers, these numbers here are algebraic integers, and they're from a countable form. Okay. All right. So. All right. So everything I was doing here, and even here, I was counting, and if you push the thing down and it bends a little bit, I was not paying attention to bends. Okay? So let me show a picture of what you see in an actual So this is an actual fluid. And so this is a story. I'm confessing here, and I didn't ask permission. But anyway, so this only shows a picture, and this is a fluid that you put a little bit of dye on it, and then it has some protocol to mix it, and there are three rods here that mix the fluid. And they move exactly like I said in that break. Two of them move like this, and the other move like that. And then what you see here is very much the limit of this thing, except that you see this entrance here, this thing coming in right there. In the other picture, you see it on top because there's a reflection of this picture here. I didn't draw it. But anyway, so that's what you see. That's the lamination. After you've done this many times, and what I am going to say is that in the other picture, I wasn't worried about these extra kinks here. I was pretending that they're not there, and I was straightening everything out, saying that this thing is a rubber band. Right? But now, the kinks are there, and you may want to actually pay attention to them, because this comes up, for example, if you study the Hanon family in R2. And I haven't got to C2 yet, but I want four-dimensional person. All right, so this story here of the Shimomoto story in certain classification is a story that's up to isotope. Okay? And there's a nice, beautiful theorem of person that goes with it. So now the other, and that's the story up to isotopy, but if you don't do the story up to isotopy, and you have to, you want to take into consideration these kinks, you need a different setup. And the setup is the following. We have a surface, a self-map of a surface, and you start with a Borel probability measure, which is F invariant. And you want the Borel probability measure also to be positive on open sets and non-atomic. So we have a surface with a Borel probability measure, which is nice, that is the entire surface positive on open sets and doesn't have atoms. Okay? And then you have two Trinitworth measured turbulation. Well, the definition of turbulation is a decomposition of a positive, of a full measure set into one-dimensional lines. That's what a turbulation is. It's not a lamination because you can have kinks everywhere. You can't talk about local charts. So there's something called a turbulation. You should think of a turbulation as a lamination that may have kinks everywhere. And then, but not only that, these turbulations have measures. These lines, like I said, in one dimension, having measured on a line is like having a geometry tool, but in that case, just think about the measure at this point. And so these lines have measured like that, have measured like this. Even if there are kinks all over the place, you can take the product measure and you obtain, so by hypothesis, you obtain again the measure you started with. And there is a real number, which is like the growth number, which makes, one of the turbulations gets expanded by the factor S, and the other one gets contracted.
Why do you call them turbulations?
Because they can have kinks everywhere. Because you expect things to have you don't expect to be able to have nice.
So even locally.
Even locally, we have kinks everywhere. There's many kinks, so we don't. So the definition.
Otherwise, it would be lamination.
That's right.
These are not.
No, these are much more complicated things, and that's what you expect to see. Or the context. Okay. All right. So now I get to the point here. So people say talks should have proofs. I'm not sure I'll give a proof, but I will give a statement. So in the pseudo-nozzle story, pseudo-nozzles have Markov partitions. Markov partitions are finite objects, and therefore the pseudo-nozzle story has only countably many maps. Okay? There are countably many pseudo-nozzles in the world. But if you want to describe something like the Henon family, or the quadratic family, or the 10th family, if you want to describe, or the quadratic family complex, I mean, there are uncountable many parameters. Parameters vary in C, and there are uncountable many different dynamics that you have to account for. So if you want to make models for such uncountably many maps, you need uncountably many models, or else you're losing stuff. Okay? So these measurable pseudo-nozzles that are just defined have at least the advantage of being an uncountable thing. Okay? And moreover, in fact, you can produce a one-parameter family of such map of measurable pseudo-nozzles. These are called measurable pseudo-nozzles, which are homeomorphic with two sphere with these various measures and various turbulations and etc. And the dynamics of this family mimics the dynamics of the 10th family. So you construct it, so this construction produces a family of sphere homeomorphism that is very much, like the precise analog of the 10th family in dimension 1. Produce, and this is not just a blah blah blah. This mimics the dynamic of the 10th family. It's in a very specific sense that this family of NPAs is really it is essentially the inverse limit, natural extension of the 10th family, up to some collapse. Because the inverse limit is some canvas there, it's an infinite dimensional space, and here you really have a family of maps of which here. Okay? All right, so let me just go on to how much time. So let me just, then I can say these questions here. So I believe that measurable pseudo-nozzles are exactly, or in fact, the correct analog of the piecewise linear constant slope map in dimension 2. Okay, so the 10th family is not just that it's a 10th family, it's that it has constant expansion factor. It expands constantly everywhere. The fact that it's up and down here is relevant to the expands by factor S. And these pseudo-nozzles, or these measurable pseudo-nozzles, they have constant expansion constant expansion and constant contraction everywhere. That's the and there's a suggestion here with people who work in different dynamics. If you have a C infinity surface diffeomorphism, it's possible to take a quotient that will produce such a measurable pseudo-nozzle. Well, not quite. You really have to. You should require that there's a single homogeneous class. So there's some condition here that your dynamical system should really be an entire dynamical system. It can't be divided into independent pieces. So as long as you have one non-wandering set, let's say, is one piece, which is so-called the homogeneous class, then there's a quotient that produces a measurable pseudo-nozzle. So these measurable pseudo-nozzles should be quite pervasive. All right, so let me go up in dimension by only one. We can't get to dimension 4, but let's get to dimension 3. Right, so there's a theory due to Mario Bonk and Daniel Meyer for so-called expanding Thurston maps. So a Thurston map is a ramified cover. So you start with a sphere and you have a ramified cover of the sphere. Now, so you take the ramification points and you require that under iteration they have finite orbits. This is called a Thurston map. And then so that's what a Thurston map is. And you call this Thurston map expanding if you can divide the sphere, say, into two pieces by a Jordan curve, and you think of the sphere then as two disks, the one and the other. And it's expanding. If you take three images of these two disks, they become smaller and smaller, and go down to points. That's the definition of expand.
But it is not the division like a Markov. Pullbacks do not parallel one or the other.
Well, here,
Just shrink exponents.
well, I think that's a possible definition, but you can actually apparently
Maybe one can make
you can actually find an invariant curve that has a problem.
Yeah, that's my question. That's fine.
Then it becomes more complicated. There are conditions which are equivalent, but it's a theorem that you can actually find if it's satisfied the property. You can actually find one which is invariant. So this becomes more complicated. And then again, you count the number of pieces at every iterate, and then this has some sort of a growth number again, and then you take the limit, you take some 1 over n power, pass the limit as n goes to infinity, and you again obtain some sort of combinatorial extension factor. And this is not, I'm again being impressionistic here, because you really should count, going from one side to the other. There's some number here which is not trivially equal to the degree. Not quite the degree, but in any case, something like that. There's a growth number here, combinatorial growth number. And then again, this is their theorem. So if, so if this number, well, I didn't say this anywhere so far, but you always have to assume that the growth number is bigger than 1. You don't want trivial growth rate. Again, so if the growth number is bigger than 1, then there are such things as these called visual metrics on the sphere, and this is very much in parallel to the global hyperbolic discussion. You can think of the sphere as a sphere at infinity for some hyperbolic type space, and you again get some sort of a geometry on the sphere, which is called a visual metric. And again, I mean, once you construct these visual metrics, the map itself becomes uniformly expanded. With this geometry, now you get a uniform expansion by factor S. Okay, so the third and fourth domain is mentioned two operators. You can mention two still. We get a structure on the two sphere, and the map becomes a linear expansion. All right, so Banach certain maps are analogous to both critically finite multimodal interval. Okay? So these guys are just the sort of complex version of multimodal post-critically finite maps. Right, so I've said these things here, and this is the question that I want to talk about. But so let me go now truly to dimension 3. So I'm going to take this Bottommeyer construction and maybe do something with it, which will produce a three-dimensional space with geometry. Okay, so let me give an example. So we're going to start with an expanding Thurston map, and we're going to associate to the expanding Thurston map, which is an endomorphism, is non-injective, and just like tent maps or multimodal maps are non-injective, we'll now upgrade, so to speak, this to a three-dimensional space where you'll have a map which is a homeomorphism. So we have the two-sphere and expanding Thurston map, and then you can produce something. But let me do the construction in one example here that it's like a little bit easier. So we just a quotient, again a quotient by an evolution. So what's this one here that you can do in dimension in front of you. In fact, I even brought a model. Okay, so here's the map. Okay, so this is the sphere through the pillowcase. So two squares glued by the boundary, and then the map is like this. You expand each one of these squares by 2 in all directions, and then each one covers this white one covers the front face here, this black one covers the back face there, the other black one covers the back face, and this white one covers the front face, and then it's ramified over these 4 points here. And it turns out that these 4 points here map to 0, so this is the typical case of a post-predicting finite branch, ramified branch cover here. Okay. Now, so this clearly has a front-back symmetry, which I'm going to codify. And I hope you believe me that, under the symmetry, what you're doing is this: you take a square, you grow it by 4, and then you fold it like that. So here's the predictive model. And you take a square, and then you fold it like this. I need to do it all in the same. So you fold it like this, and then you fold it like that. And then you fold it like this, and you fold it like that. But except that you fold it, and then you stretch it back again to the original size. Okay? Then keep doing this. Okay? And that produces something. And what it produces is the following. You can actually thicken the square, which is just a square, to a slab like that, to a prism. But you thicken the square and you just give it some thickness. Okay? And then how does the map work? Well, you define the height by 4. You make it flatter, and you expand the both boundaries by 2 each, so you have the same volume. And then you do exactly what I'll tell you. Fold it in 4. And you can keep doing this, but so if you want to fold this in half now, if it's dimension 1, you can actually fold it. But if it's thick, when you fold it, it kind of rips. You have to tear it open to be able to stack these things precisely. So the way to do this is that you have to glue, right? So the places where you rip, you have to identify these points in the image, and what turns out to be the case. So this is like this boundary here, the vertical boundary of these 4 squares around the slab. So that's how the identifications turn out to be. One of them you just fold in half, top to bottom. Another one you divide in half and fold the top and the bottom. And then in the other one, you have to do infinitely many folding. So here are some of them, and those are mapped to here, these are mapped to there, those are mapped back to there, and you have to do infinitely many folding. But in any case, you do that, and that still leaves the top and the bottom, and then there's a recipe for how you should fold the top and the bottom as well. For the top face, you just fold in half, just like you do here, fold it in half. But that means at the bottom, if you look at the bottom, you bring these backwards, you end up having to do infinitely many folds again. And you fold, you divide in half and you fold, you divide in half and you fold, divide in half and you fold, divide in half and fold, and etc. You end up having to do infinitely many folds. And after you do all those, guess what space you get? Well, it's a three-dimensional space, right? With these infinitely many identifications along the boundary. What? It's a granted. Sorry, it's a three-sphere. And the reason it's a three-sphere is, well, there's some yeah, so you have to prove it, and proving it is. All right, so I won't get into this. Right, and then like you mentioned, 1 and 2, there are many questions that we don't know how to answer. So the theory in dimension 1 and 2 is much better understood. In dimension 3, what kind of structures? Because there's a whole, world out there of structures, geometric structures on 3 manifolds, parabolic structures, and all sorts of interesting things. But we don't know exactly from this first principle construction what kind of geometric structure you end up getting. Okay, so that is the end of my talk. Thanks very much for listening.
So,
I have a silly question. So So is this construction somehow generic? So because there was some, well, there was folding done in some particular way. So if you do this folding in like, I don't know, in a different way, you always get a free sphere.
In this case, when you're doing something that's symmetric, yes, you always do. But well, you could obviously.
I'm thinking you can get like divide it into 9 squares and just fold it in a different.
Yes.
You always get
provided that you can do it in free space like that.
Okay.
You have to be able to perform these folds in free space. Because you know the technical term here is pseudo-isotropy or shrinkable upper semi-continuous decomposition. So there's some technical issues here that you have in order to prove that the quotient is a free sphere. You need to be able to perform this by a pseudo-isotropy in R3 or in F3. Now, in general, this is in the presence of a symmetry. In general, you can construct a 3-manifold, and the 3-manifold will have a singular point where you know the weird stuff ends up being hidden. But you know, most of the space is, you can locally prove that this is a 3-manifold, but there's a bad point somewhere, which under this, if in the presence of this symmetry, the bad point miraculously disappears and it becomes a 3D.
Some ideas are in the paper from which all from which you may took. In the paper in Hayshinsky and Pilgrim, where there is also some extension of a mapping to 1 dimension higher using a graph which is constructed there, and it is kind of realization of inverse limit in extension to the graph, which has a limit being this set.
So I talk about this. I never.
Actually, we have with Anna and other authors a paper where we use also other consider also other measures, because here you just count number of something like again kind of maximal measure. You can extend it and then we start some probability properties. But what I wanted to say that the idea, the geometric idea, is what you tried to explain us also, and which was kind of a dream, we know how to extend the action of Kleinian group on the sphere to action on the solid ball. And here is also in what you were talking about and what is in these graphs giving visual metrics. It's also kind of realization of this dream, how to realize inverse limit. This is
Hayshinsky
and Pilgrim.
They
don't. What they do is kind of.
I work with Daniel Meyer.
Okay, but I'm not specialist in this area, but I know all these people work it a little bit independently.
Right, and Daniel says, you know,
maybe Mario Banks.
There are similar things to Kevin and Peter, and then I never. I said, well, okay, so you should tell me what you've done. I don't need to look at it, but I'm sure.
No, the main things are in this Hayshinsky Pilgrim. What we did, we just went further than Thurston, just general rational measures, and not only maximal measures, but any measures. Nevertheless, the constructions are taken from Pilgrim and Hayshinsky. Here you also started from dimension 1, then dimension 2, and then you try to say something about realization of inverse limit in dimension 3. So I say that this graph, which is in that paper, somehow realize this extension to dimension, to higher dimension, where the tree is placed there in bigger.
Okay.
Sorry, I'm vague now, but.
Okay.
Kaczynski premium, there is an asterisk which appeared maybe 12 years ago.
And remember the beginning of the millennium.
Even 20 years. I don't
know.
know. But it's a
Not recently.
special volume of us asterisk.
Okay. Well, right, I know of it, but then the always says, oh, I've done very similar things. I said, okay.
I don't know this.
I don't have to read it. Right?
This pillow example you discussed, it was
Right.
also presented there. It's not invented there, it was taken from earlier thing.
But, you know, the first example we have, so in order to produce this very elaborate model here to show you, you have to have a square. And, you know, there are no square sheets of paper typically, so you have to do very difficult, you know, measuring to get a square. But so there is the other thing, if you take an A4 piece of paper, then you can fold it in half like this. And then if you turn, then you can fold it in half again, and turn, fold it in half again. And that was actually the first example that we worked out, but it has this turn, which makes things slightly less easy to see. So I've grown up to get the square. Okay, so thanks.
Any other questions, comments? Not, present camera again.
To taki mędrny.